Hello, today I'm going to talk to you about Notes 10.3 or 10-3, and this has to deal with special segments of circles. So there's a few different things we're going to go over, and the first of those is when you have two chords intersecting inside of a circle. So I'm going to draw a couple of chords. So this is the exact situation. You're going to have two chords intersecting inside of a circle. So here's one chord, and I'll just draw another one. Doesn't really matter where, as long as they're chords, meaning they're segments that have both ends on the circle, both endpoints on the circle. So we have two different chords here, and it says the products of the segment of one chord is equal to the product of the segments of the other chord. So it's actually a pretty simple relationship. We could call this first chord as having segments A and B, and we could say segments C and D are part of the other chord. So this is a very simple relationship. We just say A times B is equal to C times D. And that's really all there is to it. This one's really easy to remember. Of course, we can try some examples using real numbers. So let's try example 1. Here we have two different chords intersecting, and again, if there are two chords, the only way they could intersect would be inside of the circle, right? So inside is actually one of the key words that you're going to want to remember. So again, here we have an intersection inside of the circle. So we can say this is point B where they intersect. If you really wanted to give it a name, you could say segment, or the length of, AB times the length of BC is equal to the length of EB times the length of BD. And when I say the length of, that you could also say the measure of AB times the measure of BC, and so on. Okay, so fill in what you know. AB has a measure of 5. BC has a measure of 12. EB, in this case, is the one we're calling X, and BD, we're going to call it 10. So this is a pretty simple formula. You could say 5 times 12 is 60, and 10 times x is 10x. Divide both sides by 10. X is equal to 6, or 6 is equal to x, either way you want to write it. So that's all there is to it. And that one's a fairly simple one because this was just a single x, unknown term x, and it was a very simple expression too. There was nothing being added or subtracted from the x. So let's try a little more complicated one. Now that you know the general setup, we're going to just multiply segments of the same chord. So here we have x and x plus 10 on the same chord. And that's going to be equal to the other way, x plus 1 times x plus 8. And the hardest part about this one is you're going to have a little bit of space here. You need to write maybe a little smaller. But the other hard part is you're going to have quadratics out of all this. So you're going to distribute this x. Maybe if you need to, write some arrows to help you know that you're distributing this. This is x squared plus 10x on the left side. And then you're going to use FOIL for the left side, for the right side, I mean. So first means x times x is x squared. Outer, 8 times x. So add 8x. Inner, plus 1x. Should have just written x, but anyway, 1x or x, either way. And then 1 times 8 is 8. So combine your like terms. Actually, before I combine, let's combine them anyway. X squared plus 10x equals x squared. Okay, the only one I can really combine is 8x and another x is equal to 9x. So I've now combined, and you would want to combine everything else that you can. Turns out you have an x squared on the left and an x squared on the right. They exactly cancel each other out, which is great. And you're left with 10x is equal to 9x plus 8. This is actually almost ready to solve. If you just subtract 9x from both sides, you get x is equal to 8. And that's actually your answer. If you ever want to plug it in just to check, you could. You'd get 18 times 8 equals 9 times 16. If you calculate those, they should be equal to the same thing. So that's where you have two chords intersecting inside of a circle. And there's another situation we're going to talk about next, which is where you have two secants. And they're going to intersect also. But remember what secants are. These are kind of like lines that intersect a circle at 2 points. And that means they're also coming outside of the circle. So I'm going to get a ruler actually this time around, because these are going to be kind of long lines. And I'm going to draw a secant going there, and a secant going there. Now I could extend these secants to go farther to the right, but it wouldn't actually help illustrate this, so I'm just going to leave it like that. So it says when two secants let's see, I'm not sure if that's, I think, yeah, secant segments. Anyway, they're not complete secants, I guess, because we didn't draw the rest. But the main point is when two secants are drawn to a circle from an external point, that's really the key word here. This is my external point where they intersect. So the product of one secant segment and, so yeah, this is the secant segment, and we're going to multiply that. So yeah, the whole secant segment, and that means actually from here where they intersect all the way to the other part of the circle. So the product of one secant segment and its external segment equals the product of the other secant segment, the whole thing, and its external. Okay, so this one's a little bit trickier to explain, so I'm going to have to use some letters, and we're going to call these segments A, B, C, and D. Okay, so here's the relationship. The product of one secant segment and just its external segment. So this A plus B together makes up this whole secant segment. That's what we're talking about. The whole thing. We're going to multiply that by just its external segment, which we're going to call the outer. And that's equal to the same thing for the other one, the whole thing times just the outer. So I'm going to write that over here. This is one way you can remember this. W times O equals W times O. That's the way you're going to probably want to think about this. And W stands for the whole. The whole times the outer part is equal to the whole times the outer of the other. So the whole segment, A plus B, times the outer, which is just A. So let's write that down. A plus B times just the outer is equal to the whole thing of the other one. The whole thing for this other secant is C plus D times the outer, which is just the C. And yeah, so there you go. And it might help if I indicate this is the outer, or just this part right here is the other outer. Whereas the whole thing would be all of it added together. Okay, so whole times outer equals whole times outer. That's really what you're going to want to remember for secants. So let's try example number 3 here. We have that exact situation. two secants. See how they both intersect the circle at two spots. This top one might be harder to see, but it intersects at both G and H. And both of them intersect at the same external point, which in this case is J. So here's how you're going to do this. Again, whole times outer equals whole times outer. And what does that give you in this case? I'm going to say the whole thing for this top secant is x plus 8 times just the outer part of that is just my 8 is equal to the whole thing of the other one, 10 plus 6. 10 plus 6 times just the 6. Well, I'm going to have to distribute on the left side, and I probably want to combine on the right side. So 8 times x is 8x, and positive 8 times another 8 is 64, positive 64. This one I'm going to combine 16 times 6. So 8x plus 64 equals 16 times 6 is 96. So now it's just a two-step equation. I'm going to move the 64 over, and what I do to the left I got to do to the right. That's gone on the left. You have 8x is equal to 32. Divide both sides by 8, of course, and you get x is equal to 4. So that one wasn't too bad. Whenever x occurs inside the circle, you're only going to see it once. Notice I only had the x appearing one time. If it was on the outer segment, then you would actually see it both in two different spots. So this was the easier case. And we're going to try one now with the harder case where, notice the outer segment, RT, is actually the unknown this time. So it's going to appear twice. I always encourage you to write down the formula that you're going to use. In this case, it's W times whole times outer equals whole times outer. What is my whole thing? For this first one, it's x plus 9. The outer is x this time. Whole times outer for the whole for the other one is 4 plus 5. And why don't I just write that down? 4 plus 5. And outer is 4. So there we go. Multiply, which means you're going to distribute this x. X squared plus 9x. And I'm going to go ahead and simplify this one again. That's 4 plus 5 is 9 times 4. So you got x squared plus 9x equals 36. I can't really solve this very well unless I move the 36 over. So I'm going to move subtract 36 from both sides. I get x squared plus 9x minus 36 is equal to 0. And then really, I think this one's probably easier to solve just by factoring. 36 is 3 times 12, negative 3 times a positive 12. So if you do that, you can use your x method, negative 36 and then 9. So that gives you 12 and negative 3. So I'm going to say that x minus 3 times x plus 12 equals 0, which means x could be equal to 3 or x could be equal to negative 12 when you solve each of them. Set each of them equal to 0, of course, and that's how you solve. And what do you get? You have x representing a segment length, meaning it cannot really be a negative. It doesn't make sense. So although you might have said it could be, x could be positive 3 or a negative 12, really the negative 12 doesn't work because you wouldn't ever have a negative segment length. So let's try this. 3 and 9, that's 12. That's the whole thing is 12 times your 3 again, that's 36. And you get 9 times 4 is also 36. So yes, this actually does check out. Okay, so that's two secants intersecting outside of a circle. There's one other situation, and that's where you have a secant and a tangent. Remember, a secant intersects the circle at 2 points, whereas a tangent intersects the circle at exactly 1 point. So let me try to draw this again. I'm gonna try to draw a tangent first, because that's probably the harder one for me to draw. Okay, so I'm going to say my tangent's going there, and it's going to intersect with a secant that actually does intersect the circle at 2 different points. Sorry, my ruler moved on me when I was drawing, but that's pretty close. Okay, so let's read the formula here. When a secant segment, so that's this top one, and a tangent segment, that's the bottom one, are drawn to a circle from an external point, that's where they're intersecting, right here, outside of the circle. That's why it's called external point, because they're intersecting outside of the circle once again. The product of the secant segment and its external segment, that sounds familiar, whole times outer, is equal to the square of the tangent segment. Okay, so I really think, although it says the square of the tangent segment, I really think it's easier to think about this in exactly the same way that we just learned. So when you had 2 secants intersecting at an external point, you had whole times outer is equal to whole times outer. This actually works just as well for this one, even though it's a different situation. You have a secant and a tangent. So what is the whole thing for the secant? First of all, let me label these. Let's call this A times B. And then the tangent one, just to be a little different, let's just call this segment T for tangent. Okay, so let's say A is really my outer segment. T, this is my tangent. The tangent, whether you realize it or not, the whole thing is actually, you could consider this to be outside of the circle. So the tangent is already your outer segment. So I'm going to say this, whole times outer equals whole times outer. Well, in this case, what is my whole for the secant? A plus B times, in this case it's just A, equals whole thing. The whole thing is actually T. What's the outer part? Same. They're both T. So it's T times T. Which is why the formula says it's equal to the tangent squared. Okay, so A plus B times A is equal to the tangent squared. So if you want to just think of it as whole times outer equals whole times outer, that is perfectly fine. But for the tangent, the whole segment and the outer segment end up being exactly the same. So it's actually a much simpler formula. It's just equal to the length of the tangent squared. And this is the tangent segment, by the way, from the external point to where it intersects the circle. Okay, so we have 2 more examples. And again, one of them is easier than the other. Let's just take them one at a time. So what do we have here? We have a secant, the 7 and the x, and then a tangent, which is just has a length of 8, the tangent segment. So let's just use our formula. Whole times outer equals whole times outer. And I'm going to go again with the secant on the left side. So what's the whole thing? 7 plus x. That's the whole thing. The outer part was just the x. Notice the x is on the outer, which is not as simple as if these two were swapped, because then x is going to appear twice, and it's going to be a quadratic. Well, what is the whole thing for the other one, for the tangent? The whole thing is 8, and what's the outer part? Also 8. So that is all ready to go, and now we can just distribute. I'm going to distribute this, I guess I'll go in order. 7 times x is 7x. X times x is x squared. And then 8 times 8 on the other side is equal to 64. And I want to rearrange this in normal order. So I'm going to move my x squared to the beginning, plus 7x. And then the 64, I'm going to subtract from both sides. and I have something that I can work with. The only thing is 64, this is not one that really works with the factoring. You cannot really solve this one with factoring. So what we're going to do is instead use the quadratic formula. And let me remind you what the quadratic formula is. That is x equals negative b plus or minus the square root of b squared minus 4ac, all of that over 2a. Okay, in this case, my a is the coefficient in front of the x squared. In this case, a is just equal to a 1. My b is the coefficient in front of the x term, so b is equal to 7. And c is this constant. Don't forget the negative. C is equal to a negative 64. So I have a, b, and c. I just basically need to plug them into this equation. So x is equal to, let's see, negative 7 plus or minus the square root of 7 squared minus 4. A is a 1. C is a negative 64. So I'm going to have to be careful with my negatives here. I have a negative and another negative. And then over 2a. So that's 2 times 1, really. Oops, sorry, I wasn't on the screen. Okay, so that is my quadratic formula with the numbers filled in. Now I need to simplify that. I'm going to do that right now. And I'll say x is really equal to negative 7 plus or minus, okay, this is going to be inside the square root. I got 7 squared, which is 49. Negative 4 times 1 is still negative 4. Negative 4 times negative 64 is going to be a positive 200, is that right? 256, actually, yeah. This should be 256. And the bottom was 2 times 1 is just 2. Okay, so we're getting close. X, I just need to simplify that radical. X is equal to negative 7 plus or minus the square root of 49 and 256. That's going to be 305. So I have the square root of 305 divided by 2. And that's really your answer. So what you're going to have to do is take this in turns. Let's just, this is really your answer, but there's 2 of them, of course. One of them is going to be positive and one of them is going to be negative. So if you plug these into your calculator, let me just do that now. I'm going to do negative 7 plus the square root of 305. And yeah, it would have been better if I had wrapped all that in parentheses. Let me insert a leading parentheses. And close it all up, divide that by 2. So I'm going to get one of my answers to be 5.2. We're just going to round to 5.2. So x could be equal to 5.2, or x could have been equal to, I could have done negative 7 minus the square root of 305. And then close my parentheses, divide that by 2. That would have been the other answer of negative 12.2. And then really that's your answer, except you need to step back and realize, well, what is x representing? X is representing the length of a segment. Can I have a segment with length negative 12? No, I really can't. So that means this is out. And the only answer is this one. And really, this is an approximate answer. It's not the exact answer. So this is an example of using the quadratic formula. And again, you're going to want to know that the quadratic formula is negative b plus or minus b squared minus 4ac, the square root of that, over 2a. Okay, so let's try another one where I think we may end up needing the quadratic formula once again. So here's number 6. Again, I'm going to say use whole times outer, because this way you only have to remember the chord formula, and then the same formula applies to both secant and secant tangent, which is great because that's one less thing to remember. So here's my secant at the top. Whole is x. The whole thing is actually x plus another x plus 4 times the outer, which was just an x in this case. And that's the secant. That tangent is just 10 for the whole tangent. The outer part, again, is always going to be the same. So that's just another 10. So I'm going to distribute this, or I'm sorry, going to combine like terms. 2x plus 4 times my x is equal to 100. I'm going to distribute this x to both of those. So I get 2x squared plus 4x is equal to 100. And get everything on one side. So move my 100 over. 2x squared plus 4x minus 100 is equal to 0. And here we go again. I now have a is equal to 2 this time. B is equal to 4. C is equal to negative 100. So my quadratic formula, remember, is x would be negative b plus or minus the square root of b squared minus 4ac over 2a. Plug in what you know, which is everything. X, I'm going to carry this over to the left a little. X is equal to b is a negative b, so that's negative 4 plus or minus the square root of b squared, so that's 4 squared minus 4, a in this case is a 2, c we said was a negative 100, and over 2 times a I just said was a 2, so 2 times 2 on the bottom. Okay, well, we just need to simplify that. X could be equal to negative 4 plus or minus. I'm going to focus on the radical now. 4 squared, of course, is 16. Negative 4 times 2 is negative 8. Negative 8 times negative 100 is a positive 800. And that's it for that. So then we just need to simplify the bottom. 2 times 2, of course, is 4. So if we carry this through a little more, we get negative 4 plus or minus the square root of 816. So this is not a perfect square. That's why, I didn't say it earlier, but that's why we are using the quadratic formula, because this doesn't end up being factorable. Those numbers that I started with right here are not actually factorable. And that's why we're using the quadratic formula. So plug this into your calculator. Negative 4 plus the square root of 816. All that divided by 4. X could be equal to the positive number, which is 6.1, approximately 6.1. Or if you do the minus, negative 4 minus the square root of 816, all that divided by 4, you could get a negative 8.1. And of course, x represented the length of a segment. So again, that negative is out, not going to work for our solution. So we're just going to say x is equal to positive 6.1. And that's really all we need to do for this kind of problem. So try to do your homework using these things that you just learned, and hopefully you can apply all of these lessons.